Okay, let's begin. We are going to figure out how to do the last problem on probability set 2. Problem 7, rather. Did anyone actually figure out how to actually do that one? In groups? You guys figure it out? Did you guys get to it? Did any group actually get to this? Yeah? Well, what did you do?
What I did wasn't probably like the way you would do it, but what I did is I took 0.7 for the ones where you make 10.
Yeah.
That was the first part, right?
Yeah.
I just did 0.7 to the 10th power.
Okay.
And then the other one was make at least 1. Right?
Yeah.
For that one, I did 0.3 to the 10. That would be the chance that you missed that.
Yeah.
Take 100% minus that percentage.
Yeah.
And
What are the other ones? 3 or 5?
For that one, what I did was, I did it individually from 3 to 5. So for making 3, I did 0.7 to the third times 0.3 to the 7th, and I think I multiplied that by the amount of the amount of combinations possible.
Okay.
And then divided that over the total amount of combinations possible.
Oh, you didn't need the division there, but
I might not.
yeah, let's actually figure that out. Sounds right. Now, the first 2 answers that you told me, we are actually already theoretically would know how to do those. But I kind of want to talk about a general way to approach problems like this, because it turns out that they have it's a certain type of problem with a certain type of strategy. So what I would say, let's figure it out. Let's do an easier example, one where we can actually count a little bit easier. Suppose he attempts 3 shots. And I want the probability that he makes 2 of them. So kind of set up, tell me how you would set this up. Someone who actually, maybe one of the groups who didn't actually get to this. Like, how do you set up this problem? Same probability, the chances, the probability that he makes a shot, probability that he makes a shot is going to be 70%. He makes 70% of the shots that he makes. So if this guy were to attempt 3 of them, what is the probability that he will make 2 of them? Yeah?
Wouldn't it be 0.7 squared times 0.3?
0.7 squared times 0.3?
Yeah.
That's a great guess, but that's not actually correct. So maybe start setting it up. How would you set it up? Yeah.
Well, I was just trying to figure out the different combinations of 2 shots that you can make first. So I would do like 3, choose 2. And then so multiply that by the probability of an outcome where it makes 2 shots, which is 0.7 squared times 3.
Right. So I saw maybe one group was doing it that way, and they just said, oh, it's 0.7 to the square times 0.3 to the 1. But that actually misses a few situations. One way you can imagine this as happening is in stages where he can try to make the first shot, the second shot, and the third shot. And you want to know all the ways that he can make 2 of them. So one particular way is that, well, one way is that he could make the first 2 and then miss the third. Right? And you can talk about the probability of that actually happening. The probability that he will make the first is 0.7. The probability that he will make the second is 0.7. The probability that he will miss the third is 0.3. And we're allowed to multiply here because, how do I know I can multiply here? It's independent. The problem literally said, assume he makes the shots independently. So he could make the first and make the second and miss the third. What is the probability of that situation? Well, you multiply the probabilities because we have independence. So that's one possibility. Another possibility Well, what's another possibility? Well, he could make the first, and miss the second, and make the third. And what's that probability? Well, it's going to be 0.7 times 0.3 times 0.7. Now you'll notice that this one gives us 0.7 squared, 0.3 to the first power. This will also give us 0.7 squared, 0.3. You'll find that there's another situation. He can miss the first and then make the other two. What is the probability of that happening? Well, 0.3 is the chances that he will miss the first, and 0.7 is the chance that he will miss the second, and 0.7 is the chance that he will miss the third. He'll make the third, and because they're and they're independent, you can multiply the probabilities. You'll again get 0.7 squared, 0.3. So really, if you put the answer as 0.7 squared times 0.3, you're actually only envisioning one of these situations. You're missing two other situations. So now the question is, how do you know how many possible situations there are? Easy. Like, how many situations are there here? I mean, I know there's 3, you can count them, but like in general, how do you actually count this? Yeah? 3 choose 2. How do I know it's a combination? Well, I don't care the order that the green checks appear in. I just care that there are 2 of them, right? I don't care if he makes the first 2, or he makes the first and the third, or he makes the second and the third. I just want to know what is the probability that he makes 2 of them. The order does not matter, so I'm not thinking permutations or any other way. I just want to know, okay, if there are 3 positions and I need to choose 2 of them to be the positions that he makes, he has a successful shot, well, it's just 3 choose 2. So, that kind of tells you how you would count in general. So if someone were to say, okay, he makes 1,000 shots, what is the probability that he's going to make 739 of them? It's going to be 1,000 choose 739 different ways that that could happen. And then I can compute the probabilities for each of them. So, because also these 3 situations are mutually exclusive, he can make 2 shots in this way, or he could have done it that way, or he could have done it that way, and there's no overlap. To find the total probability for one of these situations happening is just adding the probabilities. So I can just add them. Since mutually exclusive. And so I will be adding this probability, 0.7 squared times 0.3. How many times? Well, 3 choose 2 times. 3 choose 2 happens to be 3. That's how I would know there's not some other situation that I just didn't think about. This will be all the situations. There are 3 of them because it's 3 and I'm choosing 2 positions for him to make. So that would be the correct answer. And of course, that's just 3 times 0.7 squared times 0.3 to the first power, and you'd multiply that and get whatever you get. So it turns out you can actually generalize this. We obtain what's called a binomial probability. So that's a new idea that this problem introduces, the idea of a binomial probability. How do you know you're in this situation? There are 3 things that have to occur for you to know that you're in such a situation where a reasoning like this would be the way to go. 1, you are repeating an experiment. Notice that that is what was going on in this case and in problem 7. You have this guy taking a bunch of free throws over and over. He's doing the same thing over and over. There's an experiment he's running multiple times. 2. There are only 2 outcomes, or 2 kinds of outcomes. That's where the word by comes from. By for 2. Okay? We usually call these outcomes success or failure. So in the case of making the free throws, really there are only 2 outcomes that we would care about counting. Does he make it or does he miss it? So these guys are called success and failure. But basically success here means the thing that we're looking for to happen. Failure means it doesn't happen. The opposite happens. So in this situation, in the above situation, we were trying to count how many shots he made. So we think of it as a success if he made the shot. If on the other hand you were trying to see what is the probability that he misses a certain amount, then him missing would be our success, right? His failure would be our success. It depends. Success really is in quotations. It's just the thing you're looking for to happen, right? But you're in a situation where only 2 things can happen, and the experiment is being repeated multiple times, a certain number of times. Third, the outcome of each experiment is independent of other experiments. When you have these 3 situations fulfilled, you say you are in a binomial probability situation. And notice that was happening here. The guy was doing 10 free throws. He was repeating an experiment 10 times. There were only 2 options. He would either make the shot or he would miss the shot. And third, we assume they were independent. Sometimes this is going to be obvious, otherwise you'd have to be told, because there's no reason to expect that this situation would be independent, but I gave you this assumption. Once you have these 3 things being fulfilled, a strategy like what was just described is going to work. So if we set n to be equal to the number of experiments, we set p to be the probability of success, and q to be the probability of failure, which of course, because there are only 2 options, it's literally going to be the complement probability of that. It's going to be 1 minus p. So if you know one, you automatically will know the other. And x represents the number of successes. So this is a variable that represents the number of successes. Then we can immediately obtain, by similar reasoning to what I just did, that the probability that x is going to be equal to some number k. What is the probability he will make k successes? It will be equal to n choose k, right? So out of n total experiments, I want to pick k of them to go a certain way. And in each of those experiments, success will happen k times, and failure will happen n minus k times. This is called a binomial probability, and that's a formula for it. Once you're in this situation, that is how you can compute a probability of a single number of successes. And basically the reasoning is how I told you. Well, there are n positions, you want to choose k of them to go a certain way. Each of them, because you have independence, you just multiply the probabilities in that line, you'll end up getting the same probability at the end, and you just added up the number of possible ways that it could occur, which is going to be n choose k. And that is going to be the probability. So this is a new thing now. This is a binomial probability. It's a new way of thinking about probabilities. Yes. Oh, this is the probability that the number of successes, x is just a variable that represents the number of successes. What is the probability that your x is going to be k? The number of successes will be 5. Or the number of successes will be 9. Or the number of successes will be 7. Right? So that, once you know what you want your number of successes to be, this is the probability of that actually happening. And it takes into account all the possible ways and the possible orders that the success could have happened. It's all accounted for. And once you have that framework, you'll be able to answer all such problems pretty easily. And you'll also notice that there are certain cases where it coincides with previous theories that we've had, and I'll point those out in a bit. Other things to realize here. Each situation, say for k, or a specific k, will also be mutually exclusive. From others. Right? So if I ask the question, is he going to make 5 successes or 8 successes? He can make both 5 and 8 successes. This one is going to happen, or that one is going to happen. They exclude each other. If he made 5 successes, he didn't make 8, and vice versa. So this means if I want the probability that x is equal to k1 or x is equal to k2, I can just think of this as adding the probabilities. So for different success rates, I can just add the probabilities to find the chances of this thing or that thing happening. So if someone were to ask, what is the probability that he's going to make 3 shots or 8 shots, you just find the probability that he will make 3, add it to the probability that he will make 8. That is going to be your probability. So or translates to plus here because we automatically have mutually exclusive. So we're mutually exclusive. What else do I want to say? Well, here's another thing. Also, possible number of successes will be, well, you can have 0 or 1 or 2 or all the way up to n successes, right? So you could attempt something n times and you could succeed none of those times, or one of those times, or 2 of those times. Or you can succeed all of those times. Okay, so this means you have these are the total number of possibilities for successes. And this allows us to use complements. In the sense that let's say I wanted the probability that the number of successes is greater than or equal to something, or less than or equal to something. Let's say greater than or equal to 1. Well, by this rule, it means I can just add up all the probabilities starting from 1 all the way to n. But because I know all scenarios account for from 0 to n, I can instead do a complement. I can just do 1 minus pretty much all the scenarios that haven't been accounted for so far, which in this particular case is just the scenario 0. So this is me using complements. I can do that because there are only n possible situations. This is using complements by complement probability. So, some experiment is being 100 times. What are the chances there are at least 5 successes? Well, you could do 5 or 6 or 7 or 8 going all the way up to 100, or you could do the opposite of that, 1 minus 0 or 1 or 2 or 3 or 4. Right? One way might be easier than the other way, and you should just know that you can always just account for the number of successes that didn't happen and figure out the number of successes that you want that way. Because there'll only be these n situations to worry about. Anything else I want to tell you about? I don't think there's anything else I want to say about binomial. So with that being said, let's look at problem 7 all over again. The real version, right? So he makes 10 attempts. Probability that he makes a shot is 0.7, which by the way automatically means probability that he misses is 0.3, because that's just 1 minus 0.7. And this means ultimately the situation describes is binomial. Why? The guy is doing an experiment over and over and over, taking 10 free throws, doing the same thing over and over and over. There are only 2 outcomes. He'll either make the shot or he's going to miss the shot, and these are the probabilities. So that means I can think of this in the binomial probability framework, and then I can identify my n, I can identify my p, I can identify my q. N would be 10, p 0.7. And q, 1 minus p, which is 0.3. I can then also set x to be the number of shots he makes. So him making the shot is the success that I'm going to account for. And then in part A, it was asked, what is the probability that he makes all 10? So what is this asking for? The probability of what? That x will equal to 10. That is what part A was asking us. So what is the probability that x will be equal to 10?
You use the formula.
Yeah.
10 to 10. Just 1.
10 choose 10. Which is 1. There's only one way to choose all 10 things from a group of 10 things.
Right.
Times.
And then 0.7 to the 10th power.
Times.
Just technically times 0.3 to the 0th power.
Right. Now, when this is all said and done, that's going to be 1, that's going to be 1, and you would end up with 0.7 to the 10. And if you think about this a little bit, which makes sense, right? Because technically, you didn't need a binomial probability to figure that out. Because what this is saying is that he makes the first, and he makes the second, and he makes the third, and he makes the fourth. And the probability is always 0.7, but there's independence. So we're literally multiplying the probabilities all the way down. So me just knowing, oh, he makes 10 in a row, oh, that just means I multiply 0.7 10 times. So this actually falls perfectly in line with that theory, yeah.
Like, what would be an example if it was, like, if it wasn't independent? Like,
Oh, then it wouldn't be binomial.
Well, like, what would the problem be? Like, how would it not be?
Huh?
You know what I mean? Like, how would, like, what would be an example like a problem where like it's deep, it's not independent? You know, like, I just can't, like, you know, like, how would this ever be not independent?
it's not independent whenever one actually affects the other. So for example, in real life, it would be dependent, right? Because when you miss a shot, you're actually more likely to miss the next one, right? So it actually changes. So there is going to be a case where you can't really assume there's independence, which means you can't really assume that I can multiply the probabilities, which means you can't assume that a formula like this would work. You just wouldn't think of it as binomial. Even if you have a situation that's being repeated and there are only two outcomes, but you're not sure if one outcome would affect the other, you just said it's not binomial. Like, it's not this formula. I would have to figure it out some other way. I just wouldn't worry about it. So you wouldn't think of it like this if you can't be sure that there's independence, you wouldn't even think about it in this way in the first place. Yeah, so that makes sense because we have independence would tell us to multiply the probabilities. So that totally falls in line with something that we knew before, but it's nice to know that this new formula that we constructed to figure this out actually coincides with the theory that we built up before, so that's nice. So you didn't even need binomial probabilities to actually figure that out, but it's nice that it still works out. The second scenario, probability he will make exactly 2 of them. So what was that asking? Probability of x equals 2. And that is going to be, well, we follow the formula. That would be 10c2, p raised to the 2, and q raised to the 10 minus 2. In other words, that's 10c2, 0.7 raised to the 2, 0.3 raised to the 8. 10 choose 2. That's 45. So that's 45 times, there are 45 ways if he's making 10 shots that he could actually successfully land 2 of them. And you have that. What is that roughly? By the way, while you're at it, what is that roughly? What's the percentage chance that he would make 10 in a row? Yeah? 2.8%. So I wouldn't bet on him making all 10 shots, right? There's 2.8% chance that that's going to happen. What about him making 2 of them? Percentage chance. This one? 0.14%. 0.14%? Geez, that's even smaller than he'll make 10. So if I was forced to bet on either of these situations, I would bet on this one, but odds still wouldn't be that great. The chances he'll make exactly 2.14%. If he was to take 10 free throws 100 times in a row, 0.14 of those times, around 14 of those times, he'll only make 2. However, 2 of those times, 3 of those times, he'll make all 10. What is the next one? It said the probability that he'll make between 3 and 5. What is that? What is that asking about? How would you talk about that? Yeah?
Probability that x equals 3, or x equals 4, or x equals 5.
Yes. A nice way to write that down would be something like this. X is some number between 3 and 5. Now, yes, what that means is x equals 3, or x equals 4, or x equals 5. And because we know that this is mutually exclusive, this is the probability that x will equal 3, plus the probability that x will equal to 4, plus the probability that x will equal to 5. that is going to be 10 choose 3, 0.7 to the 3, 0.3 to the 7th, plus 10 choose 4, 0.7 to the 4, 0.3 to the 6th, plus 10 choose 5, 0.7 to the 5, 0.3 to the 5. What is that? So if you're doing these in your calculators, I'll probably put each of these in parentheses just to be safe. Make sure you know how to actually use your calculator to compute this. I mean, for the fancy graphing calculators, you can actually tell it to do a range of binomials, but you don't have those. So make sure you actually know how to actually figure this out.
Right.
14.87%. I believe that. I mean, he's more likely to make somewhere between 3 and 5 than he is to make exactly 2. I believe that. On average, he makes 7. These are closer to 7. So I probably believe this. This is far more likely. It's still not super likely though. 15%. D. How likely is it that he is going to make at least 1? This is what? The probability that x is greater than or equal to 1. So remember, at least means greater than or equal to. At least. It's like greater than or equal to. Remember, at most means less than or equal to. Will he make at least 1? What are the chances? Well, this just means he'll make 1, or he'll make 2, or he'll make 3, or all possibilities up to 10. So how are we going to do that? 1 minus, right? There's no way we're going to do that. It's 1 minus the complete opposite. What are the chances that he makes none of them? Well, that's going to be 10C0. There are 0 successes, so there are 0 times where that probability takes effect, and all 10 times this probability will take effect. You'll also notice that 10 choose 0 is 1. There's one way to choose nothing from 10 things. 7 to the 0 is 1. So that's just 0.3 to the 10. And again, that makes a lot of sense. That means he misses the first, and misses the second, and misses the third. We don't end up multiplying 0.3 by itself 10 times. So we end up with 1 minus 0.3 to the 10th. And that is roughly, that's going to be high, 99 something? 99. 3 nines, and then what's your
4.
4. It's very likely. That's a safe bet. I would take that bet, right? I mean, if he averages 7, yeah, he's gonna make at least 1. Come on. Probably he's gonna make exactly 2. Not very likely. He's more likely to make all of them than make exactly 2, but not exactly a thing I would bet my life on. But again, as you can see, part D is also something you could have figured out without knowing about binomials. But the binomial way is more efficient when you're figuring out these middle cases between 3 and 5. Most probably makes 9 of them. Most probably makes less than 6. You know, these are very nice. It's a very common thing to figure, to use this situation. It shows up all the time. this. Just thinking of something that I don't have to tell you. Okay, so segue. There's the idea of something called a probability distribution. What's a probability distribution? It's a function, but let's describe it another way at this point. This is a table that lists all possible outcomes. As well as the probability of each outcome. Now you can think of it as a function where the outcomes are the inputs and the output is the probability of said outcome. So normally we'd express this as a table. So I can say x is just a variable that measures the outcome. This is called a random variable. I'll talk about that a little bit later. And then in another part of the table, there's the probability of x being some value. So your x can be x1, or the output could be x2, or an outcome could be x3, all the way up to say, let's say we're in finite math, so there will be a finite number of possible outcomes. It's worth mentioning these might be qualitative or quantitative. Meaning it could be based on some quality, not necessarily a number. Quantitative. And so pretty much whenever I can create a table that I can kind of use as some sort of reference sheet, we say I've created a probability distribution. And so this is going to be in here the probability that x is equal to this output. Sometimes we call that P1, this would be P2, this would be P3, dot, 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 this would be Pn. And you can list all of those. So, examples. I can talk about the probability distribution of flipping a coin. What are the possibilities? Well, you can get heads or you can get tails. What is the probability of each possibility? Well, 1/2 and 1/2, right? So that's a probability distribution for flipping a coin. You can do a probability distribution for rolling a fair die. What are the possibilities? Well, it could land on 1, 2, 3, 4, 5, or 6. What is the probability of each of those possibilities? Well, 1/6 of the time it will land here, 1/6 of the time it will land there. There are equally likely probabilities here. That's the probability distribution for rolling a die. I can find the probability distribution for rolling 2 dice and finding the sum. What are the possibilities here? What would the possibilities be? Yeah?
2 through 12.
2 through 12. The sum could be 2, or it could be 3, or 4, or 5, or 6, or 7, or 8, or 9, or 10, or 11, or 12. There are 12 possibilities when I roll the dice. What is the probability of each possibility? Well, there's 1 out of 36 ways that can happen. Both dice would have to show a 1. There are 2 out of 36 ways that this could happen. One dice could show 1, the other could show a 2, or vice versa. We actually did this one already, by the way, and we all drew like a probability histogram and everything. So these numbers should be familiar. There are 4 out of 36 ways, 5 out of 36 ways, 6 out of 36 ways to get a 7. And that was the most likely possibility, and it kind of counted down from there. There's one way to get a 12. That's the probability distribution for rolling a pair of dice and finding the sum. In the same way, there is the idea of a binomial distribution. Basically, it is any situation that I know those 3 things are fulfilled. There is a standard way of computing the probabilities. So here is x. And for a binomial distribution, we're usually counting the number of successes, so there'll always be integers here. There's a possibility that there will be 0 successes, or 1 success, or 2 success, or k successes, or potentially all the way up to n successes, whatever n is just some positive integer. And I can talk about the probability that x is going to be equal to one of those values. What are the chances there are 0 successes? Well, it's going to be n choose 0, p to the 0, q to the n. Chances of 1 success, n choose 1, p to the 1, q to the n minus 1. N choose 2, p to the 2, q to the n minus 2. And so on and so on. Here it's n c k, p to the k, q to the n minus k. And all the way up to n choose n, p to the n, q to the 0. This is called a binomial distribution. And every stats book that you pick up in the back, there's going to be some tables like this that are going to give you about tell you binomial distributions for certain situations. And a lot of calculators have tables like this programmed into them. So once you tell the computer, okay, the calculator, I want to compute a binomial distribution, I'm going to have 1,300 trials. I want to know what is the probability that 739 of them is going to go the way I want. It will create a table with 1,300 columns. It is going to make this computation for each of them. It has that table stored as a reference. And then once you say, okay, I want 7 successes, it's going to look up the answer in the 7th column, and that's what it's going to output on the screen. So a lot of times finding these distributions, it's going to be very convenient, very important, and it just makes our lives easier. It gives us a reference to look up. Also, when you go to stats class and you're doing continuous distributions like normal distributions you might have seen before, they have their own tables that go with them. So distributions are a very important thing. They give us a function that calculates probabilities in certain situations. Very important idea, distribution. Makes our lives a lot easier. So they're very important. For many reasons. One such reason that they're important is for an idea called expected value. Now, what is the definition of expected value? What is that? This is the average, specifically in the sense of mean average, or as close to the mean as we could get, outcome that is expected when performing an experiment. It's also a very important thing. How would you go about computing the expected value of some experiment? One of the simplest ways to compute expected value is using a distribution. So let's say I have some probability distribution. X, I have these possible outcomes, x1, x2, x3, all the way up to xn, and I have the probability of each of those. Call this p1, p2, p3, all the way up to pn. Now, of course, the probability axioms tells us that all these p's should add up to 1 and so on and so forth, but let's actually not worry about that at the moment. So let's say you're looking at an experiment that has a certain distribution of probabilities. How do you compute the average expected probability? If you were to do this experiment 1,000 times, 1,000,000 times, 10,000 times, what is the average outcome that you should expect? Here's how you actually compute it. We call the expected value, if x represents the possibilities that can happen, e to the x, e of x is how we denote expected value. So that's the notation here. And in shorthand, it's called, you put a sigma, but I'll explain what this means pretty soon. From 1 up to n. This symbol just means add things that look like this form, starting at 1, going all the way up to n. So it's x sub I, p sub I. So we're going to add these products. So x sub 1 times p sub 1, plus x sub 2 times p sub 2, plus da da da. So basically what happens is this is x1 times p1, plus x2 times p2, plus dot 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 xn times pn. That is how you compute the expected value. Why does it make sense to actually do that? Let's do an example of why this idea makes sense. Someone rolls 2 fairy dice. What would you expect the sum to be? Well, we kind of know what they all are. Let's do it the above way, by the above method. If we had x possibilities were 2 through 12. This was 1 out of 36. This was 2 out of 36. So our expected value for the sum x would be 2 times 1 out of 36 plus 3 times 2 out of 36 plus all the way down to 12 times 1 out of 36. And what do you think that answer would be? It's a lot to plug into a calculator. Yeah.
7?
It would actually be 7. You kind of know what, like when we drew the graph, that actually totally makes sense that you should expect to be 7. 7 is actually the most likely one. But using the mean average idea, using the mean average idea, we actually did a probability table for all the possible outcomes, and we know that the mean of, if you have a certain number of values, x1, x2, x3, just to remind you this, hopefully you remember this. If you have n things, you want to find the mean of that. It is, you're going to add all the things, and then divide by the number of things there are, right? So in this situation, what would have happened is, well, we know all the things that could occur. Let's just redo that quickly. Die 1, die 2. You can just write in your book, like, look back at this table for reference. To know what the hell Jhevon is talking about. I don't know what he's talking about. Okay. If you had really focused on finding all the possible situations here, we know that this was 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. Now here are all the possible numbers that could have showed up. What if you wanted to find the average of those numbers? If I look for the mean of all the numbers that show up, well, there are 36 total numbers that would show up. And there is a 2 plus, hey, look at that, there are 2 3s. So there was 1 2, there were 2 3s, there were 3 4s, and so on. You'll see I will go all the way down to getting, oh, there was 1 12, which I can divide 36 into each part, and you'll notice that I would have 2 times 1 over 36, plus 3 times 2 over 36. You'll realize you'll actually get the same thing that I had before. Which would be 7. So we kind of want to take this idea and apply it to probabilities. It turns out finding the average is exactly the same as multiplying each outcome by the probability and adding them all together. They'll both always give us the same answer. Even in situations where it's kind of weird to kind of count things and separate them like this, the idea of the expected value can help us get rid of a lot. And expected value, super important idea. It's one of those things where it's why probability is so important in everyday life, because a lot of things that happen to you, it's because what someone else expects to kind of happen, right? So if you were to go, for example, try to apply for car insurance, what actually happens when you enter your information when you're applying for car insurance? Okay, here's my name, here's my age, here's my zip code, here's my social security, because they look up your credit score. Here's this, here's that. You have all this information. What that does is it puts you in some sort of database. And then they calculate an expected value for you. What is the expected amount of money that this person is going to cost me? they do this analysis. So they're like, okay, he says he's 18. Put him in the group with all the other 18-year-olds. Put him in the group with all the other 18-year-olds in this zip code, with this credit score, with this blah, blah, blah. How much money have you spent on them over the year, right? And so they put you in this table that calculates all these probabilities. You know what? Here's the chances that he's going to cost me $1,000 in the first year. Here's the chances he will cost me $2,000. Here are the chances that he will cost me $15,000 in the first year. So they create this expected value table about you, and that's what they use to tell you to figure out how much they're going to charge you for car insurance, right? It's the same thing that they would use to know how much to charge you for your mortgage, how much to charge you for this, how much to charge you for that. There are a lot of things where you might wonder, how do they come up with this price? Well, they're like, well, if this kid is going to cost me $12,000 per year expectedly, then I should charge him at least $1,000 per month for insurance, right? Otherwise, I'm losing money, right? That's how they do it. They figure out what is the expected cost that this person is going to cost me. Okay, so to break even, that's what I should charge. If I want a little bit of profit, this is what I should charge. And so everything is kind of based on this expected value idea. And it's hard for you to see it. You'll just, even well, you're not going to see what calculations went into them choosing a price for you. But when you have someone like an actuary, I don't know if you guys know what those are. These are kind of the guys that companies hire to assess risk and to assess what is the cost-benefit analysis, right? These math people that they keep in the basement to kind of work all these things out. They're the ones who come up with these models. Here they do this probabilistic and statistical analysis, and they come up with, here's how you compute the expected value. So here's how much you should charge this person for that, here's how much you should charge this for that. These are the certain risks you should take, these are the certain risks you should not take. Oh, you can buy this stock, not that stock. It's really all expected value. What is the expected return after doing this thing? And it comes from looking at a lot of data and creating a lot of tables, which is why Excel is often talked about in this thing. This is where it's kind of at. So expected value, super important idea. So I wanted to make sure I touch on that. We are going to do a lot of examples where you do expected value. But I think the next major topic that we're going to do is markup changes. It's going to be pretty cool, I think. But for now, I want to wrap up there. That's kind of all I wanted to talk about for today. I will probably give you another probability set next time for us to work on. I don't know if I'll do all of it in class. Yeah.